Welcome back, Physics 30. This is the second part of the Universal Gravitation booklet. So I think this is where we left off, looking at the universal gravitation formula here. To figure out the force of gravity between any two objects, we need to know their distance of separation, the two masses of the objects, and of course we have this gravitational constant. So if we look at this, what is the force of gravitational attraction between a 1.8 times 10 to the 8 kilogram super tankers? There's two of them, same mass, and their centers are 94 meters apart. So if we take a look at how we set that up, we have our gravitational constant, which is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Then our two masses, 1.8 times 10 to the 8 times 1.8 times 10 to the 8, all divided by 94 meters squared. So when you work that out, maybe you can try it on your calculator, you should get 245, and to two significant digits, that works out to be 250. It's relatively straightforward there. You always have access to this gravitational constant, so it's just a matter of using the two masses and the distance of separation. B, a woman standing on the surface of the Earth, which is 6.38 times 10 to the 6 meters from its center. So we kind of, all of these, the radius or the distance of separation is always from center of object to center of object. So we're assuming that the center of the woman is negligible, so it's just simply the center of the Earth approximately to where she is. The woman has a mass of 50 kgs. The Earth has a mass of 5.98 times 10 to the 24 kilograms. What force of gravity does the woman experience? So I'll get you to figure that out. Maybe pause the video, try this equation, and see what you end up with. Okay, if you had a chance to do that, you should get 489.954 newtons, which I took it to 3 sig figs, 490, with a dot after there to indicate I have 3 sig figs. And of course, how we would have calculated this before is the force of gravity is just mass times gravitational acceleration. If we assume the gravitational acceleration on the surface of the Earth where she is 9.8, interestingly enough, we get the same answer. So we use this for the Earth if we know the gravitational acceleration, or we can use this formula here, Newton's law of universal gravitation, using that gravitational constant. So earlier in that video that you saw, they talked about finding the mass of Earth. So using the idea of Fg equals Fg, or mg equals this, g times m1 times mass, second mass over r squared. If we consider something at the surface of the Earth, like the woman for example, and the mass of the Earth, and if we have the radius of separation, the radius of the Earth, you notice here that the mass of the woman, or mass of object, whatever it is that. Those cancel off. So if we solve for mass of Earth, multiply it side by r squared, divide by gravitational constant, and then you can see we got the mass of Earth using 9.8 times the radius of the Earth divided by the gravitational constant. So interestingly enough, that is how that can be determined. So surprisingly, the gravitational field strength on Earth not only changes with altitude. For example, Denver, Colorado would have slightly less gravity than here because it is higher elevation, but it also depends upon latitude. So for example here, explain why gravitational field strength is smaller at the equator than at the North Pole. If we imagine the Earth isn't quite a perfect sphere due to the rotation, the middle part is a little bit further from the center of the Earth than at the poles. So equator region tends to bulge out, making objects further away from the planet center than at the poles, so slightly less gravity, depending upon whether they're at the equator or at the poles. Now, two other equations that we can use here that are simply derived from the universal gravitational equation. So, for example, we see that F is directly related to 1 over r squared. So if we take two equations, F1 is directly related to d1 squared, F2 is directly related to d2 squared, or you can see here that force is directly related to g, or gravitational acceleration. I can say the same thing there. g1 is directly related to d1 squared, g2 is directly related to d2 squared. So I can pick two different points on the surface of a planet or Earth and do questions involving that, figuring out the gravitational field strength a certain altitude above the Earth. Excuse me. So the idea of the inverse square rule here, of course, if an object is moved 4 times the distance away from the Earth, by what factor does the gravitational field strength change? So if d becomes 4 times bigger, that's 16, but F is related to 1 over d squared, so the force is 1/16 as great. So if you quadruple the distance, the gravitational field strength, or gravitational force, is 1/16 as great. And earlier I mentioned that force of gravity, acceleration of gravity, very similar to each other. Just a little bit of unit manipulation there, and we can determine those. Let's take a look at these questions. If an object weighs 450 newtons at a distance of 2.3 times 10 to the 4 from the surface of the Earth, so if we imagine this is the Earth, this 2.3 times 10 to the 4 is this far above the Earth, and we know it's 450 newtons up here. What is the object's weight at the surface of the Earth? Given that we're going to use the radius of the Earth is approximately 6.5 times 10 to the 3 kilometers. So to figure this out, we know this information here. Now F1, we know it's 450 up here, but the distance from the center of the Earth is the altitude plus the radius. So I have to do that first of all. How far are we from the center of this object to the Earth object? I have to consider the radius of the Earth plus the altitude. So that works out to be 2.95 times 10 to the 4. And then over here at this distance from the Earth, which is, in other words, at the surface of the Earth, what is the force, or what is the weight? And by weight, we're talking about force of gravity. So here we have F1 over F2 equals d2 squared over d1 squared. So substituting everything in, my F1 is 450, my F2 is what I'm looking for, and D2, 6.5 times 10 to the 3 squared, and D1, 2.95 times 10 to the 4 squared. So what I could do here is cross multiply, take F2 times 6.5 squared and 450 times that, then divide it by 6.5 times 10 to the 3 squared, and my equation becomes this. Overall, don't forget to square these numbers. That's a common mistake that people make, so just be aware of that. And I get 9,268.9349, which to 2 sig figs here, because everything's in 2 sig figs, 9,300 newtons. Okay. Next question, very similar. Find the value of G. So in this case, instead of using the force equation, I'll use the G equation here. So a distance of 3.5 times 10 to the 3 kilometers above the Earth's surface, the radius of the Earth is 6.5. Now, we know the G at the surface of the Earth. Assuming that we're in an area that has it being 9.8, we'll assume that's what it is. And the distance, so the 9.8, of course, is at the surface. And here we talked about weight. Here we're talking about gravitational acceleration, very similar relationship. That radius of the Earth is 6.5 times 10 to the 3. And then an altitude, 3.5 times 10 to the 3 kilometers. Add up the radius of the Earth to get exactly how far that is from the center of the Earth. And we get 1.0 times 10 to the 4 kilometers. Notice that we don't have to change kilometers to meters. We can leave it as kilometers since we're consistent and both of those distances are kilometers. So we have our equation there, G1 over G2 equals D2 squared over D1 squared. So G1 is 9.8, D1 is 6.5 times 10 to the 3, all squared. G2 is what I'm looking for, and D2 is 1.0 times 10 to the 4, and I have to square that. So rearranging the equation, multiply, then divide by 1.0 times 10 to the 4 all squared, and you should get 4.1 meters per second squared as an answer. So work through that, make sure that's what you in fact get. Okay, I think I'll stop the video there. There's only a few things to clean up here, and we'll do that in part 3 of the video. Okay, we'll see you soon.